Radar Pulse Generation Example. Abstract. This document provides a brief description of the radar pulse generation functionalities and instructions to operate the UI radar signal generation example instructions manual. Overview. This example is a generic demonstration for radar pulse modulated signals. It provides the ability to configure different pulse modulation and play the signal via a vector signal generator or transceiver using the RFSG driver. Supported modulations. This example supports the generation of the following signals. 1. Unmodulated pulse, a standard pulse with configurable duty cycle, duration, and IQ rate. 2. FM slow chirp, a LFM modulated signal with an up ramp and down ramp and configurable chirp length or ratio of the entire pulse duration. 3. FM fast chirp, a LFM modulated signal with a configurable number of up chirps where the pulse duration is 4. Spread evenly over the 5. Configured number of chirps. 6. Nonlinear FM, NLFM, a nonlinear FM compressed pulse with configurable exponential order. 7. Barker-coded BPSK, phase-coded waveforms differ from FM waveforms in that the long pulse is subdivided into a number of shorter sub-pulses. Generally, each sub-pulse corresponds with a range bin. The sub-pulses are of equal time duration, each is transmitted with a particular phase. The phase of each sub-pulse is selected in accordance with a phase code. The most widely used type of phase coding is binary coding. Selected pulse modulation. Modulation-specific parameters such as pulse duration, IQ rate, BW, ratio, order. Pulse count. This option allows configuration of pulse train. The count represents the number of consecutive pulses distant relatively to the configured PRF. Blanking. This option allows blanking between different generated pulse trains, where you configure the desired blanking time in SEC. Enable loop generation. This option allows looping over the pulse train configured until the application is stopped. The results would look as following. The binary code consists of a sequence of either +1 and -1. The phase of the transmitted signal alternates between 0 and 180 degrees in accordance with the sequence of elements in the phase code, as shown on the figure. Since the transmitted frequency is usually not a multiple of the reciprocal of the subpulse width, the coded signal is generally discontinuous at the phase reversal points. The selection of the so-called random 0, P phases is in fact critical. A special class of binary codes is the optimum, or Barker, codes. They are optimum in the sense that they provide low side lobes, which are all of equal magnitude. Only a small number of these optimum codes exist. They are shown on the beside table. A computer-based study searched for Barker codes up to 6,000, and obtained only 13 as the maximum value. It will be noted that there are none greater than 13, which implies a maximum compression ratio of 13, which is rather low. 3. Script waveforms with impairments configuration. This section allows generation of a sequence of pre-configured signals. The table contains multiple rows where each row defines a pulse signal with its required parameters and added impairments. When you click on the script assistant, a window will pop up, loaded with existent configuration. You will have the option to clear the current config, then add line by line a new pulse train configuration, remove the last line added, and save your configuration to a text file. You can equally load a predefined file on disk. When you click on Add, an interactive panel will open for you to configure the modulation parameters similar to the one in the main panel. You can use the script to generate a custom train that can include different modulations and frequencies, i.e. pulse staggering and agility. Here is an example. Note, frequency agility is not supported in this example. 4. IQ waveform. Status bar. This bar will display any error that occurs during execution. In case of error, the application stops automatically and the status bar shows the error sign with the error code.